Welcome to the August meetup. This month we are meeting the second Thursday of this month, because I won't be here starting right after this meeting. So that's why I was running a little bit behind today, is getting ready to leave with the Munchkins to get back to family in Canada. So we are under two codes of conduct here. One is the Microsoft Code of Conduct, as well as the Rust Code of Conduct. Both of those codes of conduct are very simple, very straightforward. They ask us to treat one another with respect, dignity. If you feel that someone is treating you disrespectfully, I'll ask you to let them know. And if the behavior, if you don't feel the behavior has stopped, come let me know, and I will take care of it from there. This slide deck, as always, is available at slides.com, U007D. That's my online tech alias. On all the different platforms, you'll be able to find me. Anyone here for the first time? Just by show of hands. Yeah, we go. Okay. Is there anyone here tonight who was not here for July's meeting? Yeah, so we've got a few folks for that. Okay, perfect. So I usually like to do brief introductions, and because there's an audience anywhere from 20 to 45 people that show up, I think it's important that we get to know one another. So my name is Brad. I've been working with tech for a long while now, and I got my start on a Commodore 64, playing lots of games, and how people usually get their start.
Yes, back in, please.
Is that you, Eskia?
Oh, sorry.
I was like, somebody's voice is coming through. I didn't know if that was somebody else on the live stream. Let me just do a quick check on the live stream to see if there are any guests there. We have Eskia. We do have someone. Yeah, we've got a couple people on the live stream. So welcome to our live stream attendees. This is our first time doing this, so I would love to get some feedback from you after the fact, letting us know how we could improve this going forward. Okay, so so I got my start in BASIC, and on the Commodore 64, you quickly have to transition to assembly language to do anything interesting, and so that really was the beginning of my interest in systems level programming right from the beginning. Would anyone else be interested in introducing themselves? Anyone? Bueller? Yeah, sure.
Hey, I'm Sorensen. I don't know, let's see, I started doing sysadmin DevOps work 20 years ago when I deleted my parents' Microsoft Windows partition to reinstall Linux without understanding the implications of that, and became like the house IT professional, and have just never left.
My name is Sterling Cooley. I'm here because I'm interested in a language for Rust for the cryptocurrency Caspa, and there's going to be smart contracts coming on that network, so I'm trying to prepare for that. So that's why I'm here. But I have some C++ background, so.
Looks like I'm being forced to do this. No. Some of you already know me. I'm Azi, beginner Rust programmer, and yeah, I like being here.
All right, we don't have to just do the front row. No one's going to sit in the front row ever again. But yeah, if anyone else would like to introduce themselves, let me know. Say a few words while you're here. Okay. Yeah. I'll run you over.
Hi, I'm Connor. I guess I describe myself as an intermediate Rust programmer. I'm just here to hang out and learn from people smarter than me.
Welcome. All right, so just so folks know, especially those who are newer to the group, the last time I asked, a little bit more than half the people identified themselves as being, Rust beginners. They might have deep experience in other languages. They might have not so much prior experience, but in terms of their Rust knowledge, they would describe themselves for the most part as Rust beginners. So a lot of our talks sort of tended to the intermediate and advanced stuff. And so what I wanted to do is to make sure that with such a large portion of our group as Rust beginners, I wanted to make sure that we put made a place for the presentations that that our beginners need to hear. So tonight we are dedicating the entire evening to Rust beginner talks, and it's something that we'd also like to do going forward, helping people get started with the basics, like, oh, what is a trait and what's a trait object and how do I handle errors properly in Rust? I'm used to maybe exceptions or something else. Like those are the kinds of things that a lot of beginners will struggle with. Of course, there's the what are these lifetime things and the apostrophe. There's all of those types of problems and questions for beginners as well. And we'd like to sort of have this running series where maybe one talk each meeting is dedicated to beginners. It's like kind of like a reserve slot. And then that way folks can, whether you're beginner, intermediate, or advanced, there's always something for everyone at each meeting. So the upcoming meetups, we typically meet on the third Thursday of every month. And this month is unusual just because of my vacation. November is also the second Thursday. That is because of Thanksgiving, I would assume. I don't know exactly what day that is, but yeah, I know, crazy American Thanksgiving. Yeah, just do it in October, right? So, oh, it is the third Thursday. That's right. Good point. So yeah, we'll be meeting on the second Thursday in November. But and I think December we'll be moving it to an earlier Thursday as well because of Christmas. Just so everybody knows, the group does tend to gather either outside the front door after meetings, sometimes for an hour or an hour and a half outside the front door. And also the group will go to the Flat Stick Pub down at Redmond Town Center, not too far away. So if you are interested in socializing a little bit afterward, you'll have a couple of great opportunities to meet folks and discuss whatever suits your fancy. So I'm going to do some announcements. I'm going to be taking over sort of organizing the speakers. We've been trying to find a way to get that organized. I don't know that the forums that we've been trying have been, super effective. So what I'd like to do is, like, does anybody have any talks that they would like to give to the group, either beginner, intermediate, advanced, or even just an idea? Just by show of hands, is anyone interested? Nate, you might have one. Yeah. Okay, so we've got like 3 or 4, maybe 5, 6 talks that people want to give. I would ask you guys to definitely reach out to me on our Discord. If you haven't joined our Discord yet, I'm U007D on the Discord. And what I'll do is get your name, your talk subject, what you think roughly the duration would be, and when you think you might be ready. I won't hold you to it. If it's not ready in a given month and you need more time, no problem. I have backup material that we can always use, already prepared for this. So this way we'll just have this nice backlog of people able to speak about different topics, and we can make sure that we have good beginner talks, intermediate talks, and advanced talks at each meeting. So yeah. Best way to do it is just to reach out to me on Discord. If you tell me here, I will forget, right? I see happy, friendly faces. I recognize your faces, but I certainly won't remember your online handle and be able to reach out to you. So please ping me on Discord, and then we'll get that conversation going. Second point I wanted to talk about was our hands-on embedded sessions. We have this lecture format, which is what we'll be doing tonight, but we've also been alternating every other month. This would have been a month where we did the hands-on embedded systems work. And we did 3 of those so far this year. People bring your laptops and you wire up some wires and write some code without an operating system. Is there interest in continuing those sessions? Yeah, just by show of hands. Okay. So we've got about a third, okay. Would people like simpler projects or more complexity or about the same? Okay, just like thumbs up for more complexity, thumbs down for simpler, and flat. Assembly. Oh, not assembly language, assembly of the board. Yeah, running running 4-digit LED was a lot more wires than we expected for sure. Yes, yes, it was astonishing how many wires there were. It's crazy. All right. Yeah. hmm 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 Yeah. Okay, so let me make sure I capture that so that the folks at home can hear that. So the comment was one of the a suggested topic would be hardware debuggers. These are debuggers that will grab and stop the CPU. Your computer CPU is going to do what it's going to do, but the embedded system has its own microcontroller, and the hardware debugger is yet another CPU that controls the microcontroller. And that way you can single step through your code that's actually running on your target system, just the way you would single step debug, your ordinary code with a debugging IDE. Mhm. Great, great. So yeah, Carl's second suggestion was with that project where we have 4 LEDs running and then the timing button for that game, we have at least a couple different implementations. There's interesting things like how do you build a state machine in Rust, certainly in embedded systems. What are some of the trade-offs for the different ways that you can do it? Looking at the different approaches to how the software was written in different approaches and being able to learn from the strengths and weaknesses of various different approaches. I think all of those would be really good suggestions. Any other thoughts? Oh, I think that's a great suggestion. The suggestion was that when we get together to do this, we focus this is the Rust meetup. So if you're here for Rust, you're more than welcome. If you're here for, I think C++ is next week, so we're not at the same time this particular month. Yeah, so the suggestion was when we get together to work on the embedded systems projects, we can actually learn about Embassy. We can learn about the principles of debugging and cross compilation and those principles, so that way people feel they walk away from here equipped to go work on their own projects. Then they could come back with, say, different things that they may have worked on their own, and we can do a show and tell here. So more of the fundamentals of how to write any code rather than we're all trying to write a particular program at a given session. I think that's a great suggestion. Thank you. Question is, can you do Rust on an Arduino? And the answer is yes. We are running Rust on a Raspberry Pi Pico, which is a Cortex M0, right? So it's a very small microcontroller with 264 kilobytes of RAM, and just like C or C++, it works just fine in bare metal environments. Mm-hmm. Okay, great. Thank you, guys. Those are fantastic. Third announcement would be, would anybody be interested in a Bellingham Rust user group? So for anybody here, or if you know anybody, or for those folks who are joining us from online. If you're interested in the Bellingham user group, or you like the idea of having a user group in Bellingham, so maybe you don't have to come all the way down here, please reach out to Eyes on June on Discord. They've put out a request online and asked if I would make an announcement here tonight. So there you go. And I also think we have one other announcement. So here, Carl, I'll give you the mic.
I'm giving a talk next. I'm not a talk. I didn't get the talk. I'm giving a workshop the day before the main Rust conference next month in Montreal. I'm told you should beta test your workshops, especially if you've never actually given a 3-hour workshop before. So I would very much like to get some volunteers for me to give my presentation. I'd probably give it to people in a 1-hour chunk via Zoom. So all we have to do is find the time. The 3 hours, the first, and you wouldn't have to sign up for all of them, but the first hour I'll be talking about how to port Rust code to WASM. Well, I better learn how to pronounce these. WSDI, the interface things so you can run in the cloud instead of running it on your local machine. Okay. Yeah, online people can say this too. In the second hour, it'll be how to run it with WASM in the browser, which is actually something that's useful and fun. And in the third hour, how to port your code all the way, your library or whatever, all the way to embedded. And the reason it's in these 3 steps is because pretty much every one of those steps is a prerequisite for the one before. So I would love it if you're interested and we can try to set up a time. You can find me on Discord. I don't remember what my handle is, but I'm chatty on there. Or you can send me an email. Okay, probably Carl K, C-A-R-L-K. And my email is carlk@msn.com. Thanks.
Thank you, Carl.
The question is, what level of people? You should know how to run a Rust program, but that's really all. And it's going to be, what are the extra steps you need to do to run that Rust program in a browser, in embedded, if you can at all. We'll talk about, it talks about those issues too.
Great. Thanks, Carl. I'm interested. I'd love to do that. So yeah, that could be a small problem. That could be a small problem. Any other announcements? Does anybody have anything to share with the group? Okay. All right. So tonight's talk, 2 beginner talks. Tonight's talks. We have 2 beginner talks. I gave a cliffhanger live coding presentation at the end of July's meeting, where we started to explore locks. Locks, what are they for? Mutex, woo, fancy words, concurrency. Yikes, I'm so scared. So let's demystify all of that, figure out what they're for. So we have a couple people here who are new here tonight. So I will reproduce the cliffhanger so that we're all on the same page. And then we'll continue past that. We'll try to run the initial code in different places and see what we need to do to fix up the problem. And then second, we'll take a little break. And then second, Jack will be giving us a talk that's an introduction to async tonight. So thank you, Jack. It's going to be fun. So for those who don't know, async is a part of Rust that lets you basically, I would say do more than one thing at a time, but that's not strictly correct. It's you can start a second thing before you finish a first thing, would be more rigorous. And you're like, well, what the heck's the difference? That's just a lot of words. Jack will cover all that, I assume, the entire topic. So it'll be, I think it'll be a lot of fun. All right. Any other topics or questions before we jump into our live coding session? Okay. I am not going to be able to type with one hand. I just realized that. Pretty sure these are live. Give me 1 second here to switch over. Testing. Okay, here we go. So what I'm going to do here is start with a new Rust project. I don't need any of this. Okay. So making sure I'm still showing on the screen, I should probably enlarge my text a little bit. Hopefully that's legible to everybody on screen as well as online. Okay, so I'm in an empty folder, and what I'm going to do is start talking about what are locks. So locks are known more formally as something called a synchronization primitive. And you're like, whoa, that's a big, a lot of syllables, a lot of syllables in that word. So what's going on with all of that? So what I did at the end of last month's meeting is I first showed the motivation, like what's the problem that locks solve before jumping into using locks at all. So we have a couple of folks who weren't here for that. Plus, I assume the folks online were not here for that. So I will reproduce that. Huh. This thing is telling me I'm sharing my screen. There we go. Okay. So I'll start with the cargo new, and then you can see we called it locks. And I will cd locks and start up my IDE. And locks now has a source and a main. So again, I'll try to enlarge this. Is that legible for you guys here? Okay, so hopefully this. Oh. Is it legible for you in the back? All right, good. All right, so what I did at first is I said, let's start with a simple global counter. So it's like, okay, that's great. Sounds pretty straightforward. I'm also going to set this up maybe a little bit more rigorously, for like as if it were going to grow into a much larger, more sophisticated app. So you're going to learn a little bit of sort of the industrial strength Rust techniques at the same time, but those can be ignored if you're just trying to grasp the basics of Rust. So for now, even though we have an application, I do like to start it as all the code is really as a library, and has the main, all it does is collect the arguments and then calls a function in the library. Maybe instantiates a type and calls a method on that type. But main doesn't really do a heck of a lot. So yes, I have to remember how to make a second. Yeah, I thought there's also something I have to do in cargo to make it lib.rs a separate crate, but we'll find out. That's the joy of live programming. And I've just updated to the latest version of Rust Rover, and it gives me all kinds of crashes, but it doesn't seem to matter, so we can just ignore those. I'm not. So yeah, it's been it says that a lot. You'll have your little red arrow here saying that it has crashed, but it's never actually crashed on me. So whatever they're doing to hide it is fairly good, although that is not super reassuring. All right, so I'm going to make a new file here, and Rust file, and lib.rs. And then in lib.rs, I'm going to have a module that we're going to call counter. And then within counter, I'm going to define a static variable called counter. Just by convention,
global variables, statics are a type of global variable, are written in all caps. And then I'll declare it as, say, a usize, and then I will say starts at 0. Now, what this is the global variable. We're going to be starting with a single-threaded application. This is going to make counter visible to the rest of the application. And then I'll have a method. Actually, I'll just keep it fairly simple, and I'll write the method right here. And I'll just call this one count. And this guy's job is to count to 1,000,000. In Rust, you can put underscores in any value, and it doesn't have to be in 3s if you're, from other cultures and you guys, do your delineation differently. It supports all of that. So this just lets you read all the zeros and know that we're doing from 1 to 1,000,000. And then we'll do for each. And then we don't really need our variable counter here. And we will say counter equals counter plus 1. Now, you can see here that counter is not mutable. Okay, in Rust, all your variables are going to be immutable by default. So we're going to take care of that in just a moment. Once we are all done, then count will just return. And then main's job is to start counting. So we'll call count. And then we'll say print line blocks counted to. And then we will say we counted to however many counter got to. Okay, pretty straightforward so far. Any questions about what we've written so far? This won't compile, right? Because count isn't mutable, but any questions so far? Okay, perfect. So we say, okay, it's not mutable. I can't assign to something that's immutable. What are you doing? Okay. So we jump into counter, and then we say, okay, let's make this both static, global, and mutable. For those who know about Rust, there's one rule in Rust. Rust has one job, right? That job is you can be shared. In other words, one or more people can read you, or you can be writable by exactly one party. Like you have shared or mutable, not both. And so you'll see that as shared XOR XOR mutable. That's the big shtick about Rust. So what am I doing? Very first thing we're doing here is I'm creating a mutable global variable. Okay, global means anybody can access it. Mutable means writable. That is exactly the one thing that Rust does not want us to do. So what do we get? We get an error, of course. Good job, Rust. Rust tells us that you can't use a mutable variable, a mutable global variable, because that violates shared XOR writable. So what we're going to do is we're going to abuse the unsafe keyword. A lot of people love to use unsafe and say, oh, unsafe means I can do what I want. It's really, really important to understand that that is not what unsafe is for. So we are abusing unsafe here. When you use the unsafe keyword in Rust, you are promising to the compiler that you are manually upholding all of Rust's guarantees. It is not a get out of jail free card. It is not a, now I can do whatever the heck I want. No. Your job is to continue to uphold those guarantees, but you're telling the compiler, the compiler can't statically verify that what you're doing is correct. So you are promising on your honor that you are upholding those guarantees. Of course, we don't need to do that. We know better. So here we go, unsafe. And now we can write to counter. You can see the red squiggle goes away. What else we got here? Oh, we're reading it. Remember, reading or writing, but never both? Well, even reading something that's mutable static is dangerous. So we now have a situation where we have to use unsafe even to read it. No problem. Get out here, go back to main, make my print unsafe. Geez, Rust is just nagging me. This is no problem. There we go. Look at that. And what did we count to? We counted all the way to 1,000,000. You see? That compiler is nagging us for no reason at all, right? Like, we know better. Our program is fine. Let's ship it to production. Everything's great until you get a new feature request. Could you count to 1,000,000 faster? You're like, sure, I got how many cores in this machine, right? 16 cores? Let's do this, right? So what we can do at this point now is we can change, we upgrade our algorithm, and we're going to change our count algorithm to do something a little faster. So maybe we'll spawn, I don't know, doesn't matter, 1,000 threads? Each one will count to 1,000? Okay. Actually, do I want it even like that? It doesn't matter. I don't think it matters. So let's do that. Right, yeah, we could do 16, doesn't matter. So what we're going to do is we're going to count to 1,000. And then for each time we count to 1,000, we are going to spawn a new thread. So thread this in thread, good. So how spawn works is it will take a function. If we look at the function signature for spawn, spawn is a generic function, has two generic parameters, f and t. We'll talk about each of those. You give it an f, capital F, and that f is actually a function itself. So if you've heard of lambdas or closures or function pointers, all of those will count, and you can actually pass that into the spawn function. And the spawn function will get the OS to spin up a brand new thread under the same process that you're on, may or may not be on the same CPU core. That thread will run whatever's in the function that you handed spawn. And then when it's done, when you get to the end of that thread, assuming it's not an infinite loop, then that thread will shut itself down. And whatever it did, those side effects will be left behind. So that's what we're going to do now. We're going to take our previous function, and we're going to pass that in as the parameter. If I've got this right. Okay. So that. Now, when you spawn a thread, what it does is it actually generates a something called a join handle. So that way you can track what happened to that thread. Has it finished yet? Has it terminated? Maybe you want to wait till all your threads are finished running. So you can hold your join handles and you can check the status of the thread, not by communicating with the thread directly, but by examining the thing you get back when you create the thread called the join handle. So for that, we're going to make a bunch of these. So what we're going to do is maybe store all of the join handles we get into a vector. So let handles okay. So we're going to create a new empty vector. And then we're going to, every time we make a new thread, The join handle that spawn returns, that's the T, right? It's going to give you back a join handle of type thread back. We're going to store that in our little handles vector. So handles, let handle equal join handle. And then we will, got to get the formatting a little bit more friendly here. Push. And what's this guy mad at me for? It's telling me it doesn't want to see a close brace. Really? Just needs a what? Or each has an open current. Oh, gotcha. Thank you. Yep, that's it. So give myself a bit more space with this big print. Okay, so there we go. We didn't even touch that inner line and that inner loop. We are looping 1,000 times, and last time I checked, 1,000 times 1,000 is 1,000,000. But we got 933,000. We didn't get our full count. Yeah, okay. That's a great answer. Let's do that. We'll just run it again. Oh, it's a different number now. Uh-oh. Maybe that's our problem, right? We need more threads. So what we're seeing is that every time we run this, we get a different answer, and it's always wrong. Okay, so this is the thing that we're fighting against. This is every language. Go ahead, Carl. Oh, that's true. I didn't even wait. Thank you. I got too excited. Thank you. It wasn't even done. Exactly. So let me go through there and say, okay, now that I've spawned 1,000 threads, and then each thread is gone and counted, then what I'm going to do is I'm going to wait, make sure that all my threads have finished counting, because maybe we were too quick. We jumped the gun here. So what I'm going to do is I'm going to take my handles. I'm going to iterate over each of those handles. And then for every one of those handles, I'm going to just the handle dot join, I think. All right. So the handle dot join is going to give me a result. Why isn't it just gonna just block and wait until it's done? The reason is that you want to know if your thread is still running, whether your thread has stopped, or whether your thread has panicked. So what it's giving you is a result. The result is going to be one of two values. It's either going to give you unit value, which is equivalent to void, roughly speaking. It's going to give you a unit value in the everything worked okay slot. That tells you that your thread finished successfully. Or it's going to give you an error code telling you that your thread is panicked. And so that's how you can tell the difference. And then you can use a non-blocking join. You can wait for this and check the status to see if it has exited. So we're going to need to use a slightly different loop. And the try for each will allow us to be fallible. And that now means that our count could fail. So we will say, make this guy result. And what are we going to say? If everything worked great, we're going to, there's nothing to say. Go check the count. Everything's going to be fine. But if there's an error, then, what error are we going to get back? Well, join is telling us that it's going to give us a probably, if I can get over to this thread, it's going to give us a very weird error signature. Box, dine, any, plus send, plus tick static. Whew, that's a mouthful. Why doesn't it doesn't even say error in there? So what's really happening here is it's telling you that if your thread fails, what you could get back is really any real type that Rust supports, roughly speaking. And you won't even, any real type, yes, type that Rust supports. There are some limitations to, what couldn't be returned, but that's beyond the scope of this conversation. So we can just say for now, it could return any type at all. It doesn't have to be an error type. It could be anything at all. And maybe it's going to be handing you back the poison thread or, a stack trace or something. So you could go and check the documentation and see why it's trying to be, super ultra flexible. But for now, that's not what we're going to delve into. So we just know we need to be able to handle this type of error. So we can just say that we're going to accept a box dyn any plus, was it send or send and tick static? All right, so that is a mouthful, and I apologize for beginner talk to be doing that. But if you squint and pretend this just says thread error, you'll be okay, right? For the purposes of this talk, it is not what it means. But for now, you can just pretend that that's what it's returning, and we can revisit that at a later date. So it's telling me now I can't move out of a handle. Do I need to move out of the handle? Thank you. For loops. Bah, humbug. Okay. So what did we do here? We iterated through every handle we had in our vec. And for every handle, we tried to call join. Well, we did call join. Join may have given us an error, or it gave us success. So if I go back to my main, and I will make it also fallible. Box dyn any. Okay. And now when I call count, I can early return. I can say, oh, if there's an error, I'm going to return. So we will not see any output. I mean, we will not see the count output. We'll see the error message printed if there was, in fact, an error, if any of our threads panicked. What did I do wrong here? So now I'm seeing mismatched types. Yes, I do. Thank you. You guys are quick. I love it. So here we go. We're going to call count. If count fails, the try operator here is going to immediately return with the error code out of main. And so you're going to get this. If try is successful, the result will be unwrapped by this try operator. And what's in the OK slot on this side was actually going to be a unit, which is meaningless, which means we were successful. So we're going to continue. We're going to print out what counter was. And then at the end of the function, we're going to return OK because we made it to the end. And that's going to return OK, which will give us a status code of 0 to the OS. So we got our print message. We waited for all the counting to finish. It had to have succeeded. We had to have waited for all the threads. And look what we got. It's fine, right? And so if anybody is
Okay, let's try this. If folks can hear me all right. There's no real boom, but Askia, let me know if my audio is coming through okay. I don't know if you can hear it at all in the speakers. Just a tiny bit. All right, well, we'll try something here. I'll speak to my friend here in the microphone while I try to code. Okay, so yeah, so now we are returning a unit in the OK slot, so everything is happy. We waited for everything because we saw the handles into iter, where we did a try for each, and then we joined into all the handles, and sure enough, we did not get our count of 1,000,000. And what's interesting is, the problem here is we have what's called a race condition, and a lot of people have heard that Rust doesn't have data races. Well, it's important to understand that a data race is a kind of race condition. There are other kinds of race conditions, and Rust does not protect you against all race conditions, especially when you abuse the unsafe keyword. But we definitely have a data race, which Rust would have protected us from. But we abused the unsafe. We said we were going to uphold all of the invariants, which we did not, and that's why we now have a problem, which we only discovered once we went to a concurrent program. Okay, how are we doing so far? Yeah, I know, it must be the M3 messing up. It's another bug in the M3. Oh yeah, this is debug mode. And so we had some fun last time because something interesting happens if you see, I'll make this here because I'm sure I'll be asked again. So one of the things that it's really important to remember if you're a Rust beginner is when you're running code, and what I'll do is show you how people normally do this. If you're normally running code, you'll say cargo. That's Rust's package manager and compiler bundler. And you'll say cargo run. And it will compile your code. It will run your code. And you'll get, that's what I've been doing when I've been hitting the green button here. But if you want to run in release mode, this is debug mode, you can do cargo run and then follow it with -- release. Then you're going to get optimizers running at level 2, level 3, and suddenly, ooh, it works. It just makes it work. It goes faster. That's right. That's why they call him debug, right? So any thoughts as to what the heck is going on? I just said we have a data race and it's gone. Now we're good. Ship it. It's in production, right? It certainly might have. It certainly. Mm-hmm. So we had one thing is that the optimizer for release realize what we're doing and sort of give us a hard coded answer. We have another hypothesis. What was your thought? If you're running in debug mode, maybe it only gives you one core. So maybe all those threads were tied to one core. Yep. Interesting. Okay, let me see if I can try to summarize that one. The supposition is maybe the optimizer is looking at the inner loop, specifically this one, and realizing that that is just adding 1,000. Optimizers inside of compilers are very advanced. And the idea then is that this is no longer a nested loop. It's just a single loop where you spawn 1,000 threads. Each thread doesn't loop. It just adds a constant of 1,000 to the global static variable. That happens so quickly that we're able to, once the thread is started, we're able to run through and quit before the next thread. The OS can actually get the next thread scheduled and running. So there's no contention. I like that. Ava? I can try, sure. We can do that. So the question is, could we test that hypothesis by just adding 1,000 in each thread rather than, doing something fancier? So let's test. Okay, so counter plus 1,000. So if the optimizer is performing this operation, unsafe, yes, forgot my unsafe. You think I'm actually doing a lot of unsafe at work at the moment, and you would think I would be all about the unsafe. Okay, so all we're doing now is we have the outer loop spawning 1,000 threads, and each thread just does one thing. It'll probably run faster than they can spawn. So back to debug. Well, let's first see if back to debug. What do we get? We made it. We made it again and again, but not that first time. Yeah, maybe it's all warmed up. So this is a classic Heisenbug, right? Like it's kind of working and it looks like it's working, but it didn't that very first time. So we know that even when we had the old code that appears to work just fine in release mode, that we actually still have a data race. It just hasn't manifested yet. And as you add more features and more features and more features to your software, you will eventually hit the condition that you don't know, and you're going to start losing data. And by then you've got 500,000 lines of code, and you have no idea where your problem's coming from. It's just manifesting that some user can't do something. That's terrible. But I know people want to take a look and see what's actually going on. So let's have a look. Exactly. So now we're going to do something real scary. I see you. Okay, so Godbolt is a really interesting website, and it will compile C, C++, Rust to assembly language, and it will show you what you're getting. The Rust Playground will actually do this as well, but Godbolt's a little fancier and is sort of known for this. So here's our function, and if we run, by the way, when we run in release mode, that's the instructions that get sent to the compiler. So if we run in debug mode, what we're seeing here is, what's wrong with it? Oh boy, yes. I've need all my accoutrements. Do I have to pub maybe? Yes. I don't think the declaration does, but I think all the usages do. We'll see. Yeah. Oh, I don't need that. Okay, compile again. Where's the compile button? There we go. All right, so now we're going to have a little look-see at our assembly language. So it's actually showing it to us in hex. Boy, oh boy, it's really given us all the data. All right, so this is actually a lot more code than I was expecting. Yeah, we're not running main. Yeah, we just have count. Yeah, that's the point. Is we want to look at it in both in debug and in release mode. So let's see. I'd like to have it highlight the section of assembly because you can see how it's colorized here, and that should correlate to sections of code here on the left. That way we're not doing a deep dive into assembly. So let's get rid of that guy. It just says purple. Maybe. Yeah, what I want to see is the colorization on the left. So when I'm clicking on this assembly language, we can see roughly what section of this is going on, but I'm not sure why that's not occurring. One of the things that Godbolt does is it shows you the relationship of your assembly language to your Rust code. That's interesting. I've not seen it. Yeah, I don't think it has to do with the lines. But go ahead. What were you going to say? Yeah. Yes. Yeah, except when I'm like hovering over 5184, you know. It usually just highlights the whole line. I'm not sure why it's not doing this today. I don't know if I have any weird setting going on here. Okay. Well, I'm going to say that the debug assembly, it's huge, and it is doing the naive thing. It is doing exactly what we said. It's not trying to optimize it. It's not trying to leave out any steps. And so this is going to be a nested loop of things, and we definitely have a data race going on here. So what I can do next is put in the optimization code. It's a -c opt level equals 3. That tells the compiler to engage the optimizers, and it's still huge. That's really interesting. Yeah, this is all I see. Yeah, this is all I see. Usually it just shows me assembly. It doesn't show me the hex, and these blocks are very well organized. So that's very odd. Well, that was less conclusive than I'd like it to be. But let us just state for the record that we definitely have a data race, even if it appears to be gone when we're in release mode. It's still there, and we could see some evidence of it when we actually optimized the code to run the unsafe, or to run the increment of 1,000 at a time. The very first time we ran it, we got 999,900. Well, we got 1,000 less than a million. So we still have the data race, even if it doesn't manifest. You just have to push your system to the right settings, and suddenly your data race will be back. Okay, so we got a problem here, and that's because we used unsafe, but we did not uphold the invariance that Rust requires. Say again? I see on the left what I want to see. Now I'm not seeing it on the right. Yeah. No, it's they're not linked left to right, so. Ah. Yeah. Okay. I don't think there's a ton of value doing compiler explorer and assembly language in a beginner talk. I just wanted to show that this thing disappears. So what do we do about this problem? How do we solve this problem? If we actually have multiple threads fighting for one resource, which can happen all the time, we have to be able to handle it. So now the name synchronization primitives might make a little more sense in that you're synchronizing access. It's like a traffic light can synchronize access to an intersection, a shared resource. That's what locks do. They allow you to ensure that only one resource is accessing a shared resource at any given time. Suspected spam. I mean, wow. Okay, so here's what we want to do next. And take this guy out. I also want to see one other thing is if we do more counting and fewer threads, do we get more or less data loss? 10,000 times 100 is still a million. So we've got fewer threads. And we go back to debug. And you see we got a lot more data loss. Okay, so we're spending more time counting and less time spawning. We get more data loss. So we go here. We go to everybody counts 10 threads, count to 100,000. So every core gets their own thread now. And we should see even more data loss. Well, a little bit less. But yeah, we're at now 113,000 out of a million. So that's, you know, just under 90% data loss. This is pretty bad stuff. Okay. So next steps, how are we doing for time? Okay, so next steps here are we need to clean up this code. So we need to use something called locks. So I'm going to use the simplest lock in the world called mutex. Before I do that, I want to explain one thing. Why is this happening? I've said it was a data race, but I haven't told you much about the data race itself. I'm going to try drawing with this. How can I make a new people? Come on. You guys know where new is on Excalibur? Nate? From share? Well, whatever. Infinite canvas. Here we go. Okay. So what's happening here? In the data race that we're running, what we're doing is we have a shared resource. And that shared resource, if I could find my text tool, is called counter. Oh boy. Okay. So this is our resource, our shared resource called counter. And then we have a thread. I'm going to try to make this box a little more reasonable. So now what happens is we come along and we have a thread. That thread has over here. So thread 1 comes along and wants to access counter. How does thread 1 do this? The first thing thread 1 does is it reads counter. It's technically pulling that into register memory. Then what it does is it increments by 1. So I will depict that. I'd like to depict that with an asterisk, just that it's getting modified. Okay. And then after the register value has been updated, then it writes that value back to the dynamic, the DRAM, the memory address where the static variable is stored. So that operation is very widely known as read, modify, write. Read, modify, write. So you can see that you're pulling the data in from memory into registers. That's the only thing the CPU can actually really manipulate is what's called register memory. Then it increments the value, and then it puts it back. So what's happening is thread 2 comes along, okay? You'll be thread 1, okay? So we set counter to 0. So what do you read? All right, you'll be thread 2. You come along, and you read counter, what do you see? 0. Now you increment your thread or your value, and then you write the number. Well, just one at a time. So you're going to write 1. So you write 1 back to memory. Now, Carl, you increment your value, and then you write that back to memory. Okay. So after that, those 2 threads have both run. The memory has been incremented, or that value has been incremented twice, but it only equals 1 because both threads started with 0, incremented it once, and then wrote the same value back to memory. That is a data race. You should not be contending for the same resource. What should happen is that while you're reading, modifying, and then writing, no one else can have access to the memory location that you're. Who's going to help you? Exactly. That's what's going on. The lock will help you with that. Okay. So does everybody have a good understanding as to why now we have that data race? Any questions about the data race? Okay. That's right. So when we, spawning a thread is very expensive. It takes milliseconds, right, for the OS to do that. But running a loop and incrementing a value can happen in microseconds or picoseconds. So what happens is when we had the loops do more counting and less spawning, there was a lot more contention. You might do 2 or 3 by the time Carl writes back his value, and then you write back your value, and you stomped all over Carl's value, and there's 9 other players going on, and you're losing 90% of the data. 90% of those writes are getting overwritten. Okay, so we understand the problem. So now what we're going to do is we are going to make sure that whenever we access counter, we're going to do it through a lock. So the lock we're going to use is the simplest lock for a synchronization primitive. It's called a mutex. It's called a mutex because it means access is mutually exclusive. Either you get access or I do, but not both. So the mutex is going to allow us to access counter. So the first thing I'm going to do is I'm going to go back to counter, and I'm going to say that counter is not a usize, but a mutex of usize. Okay, so that means that the actual value that you want to access is contained inside this other type. The type, you can't see it unless the type mutex lets you. That's a really important guarantee that Rust is providing. So how do we make it? Well, we construct a mutex with 0. Hopefully that's const. I don't have to worry about it. Yes. Okay. So mutex has a special power because mutex owns usize. Mutex, we don't have to declare counter to be mutable anymore. We are going to mutate the value inside of mutex with mutex's permission. So counter doesn't need to worry about mutability. So we'll manage mutability. That's, yeah, for today's purposes, you could say that. For the more advanced people in the room, it has to be mutable because it needs to have a state. It needs to know whether it is locked or unlocked. But you don't have to do that. That's all happening internal machinery. So now we have this shared, exclusive OR right. And now that this counter is read-only, there's no mute here. As far as the borrow checker, as far as the Rust compiler is concerned, it can give out as many copies of it as it wants to every thread that comes along simultaneously. Mutex will handle the contention, not counter. So we'll go in here. And now that counter is a mutex, you can see we can't increment it anymore. It's like, how do you add 1 to a mutex? That's not a numeric type. So what we'll do is we'll say counter.lock. That's the mutex method called lock. And what that does is it gives you a guard. No, it doesn't. Yes, it does. Okay. So it can fail as well. So for reasons, again, for panicking threads and so on. So we're going to go back to try for each because this is a fallible loop. Do I want to do that here? I might want to do the for loop just for to keep things simple. I might do that because I don't want to get into. No, we can't. Yeah, the reason why you're getting a result from that mutex and not just a guard is because if another thread had the lock while it was accessing something and panicked, divided by 0 or did something crazy, the system has no way of knowing what state your value is in. Did you read it, update it, and not write it? Were you partway back through a write? Were you synchronizing this resource with something else? It has no idea. So it's notifying you that it was poisoned, and you as a programmer can figure out what you're doing and whether or not that matters to you. So what I'll do here is I'll do is it 100,000, right? Okay. This function does not return.
I was gonna say maybe it's.
I have to. Now I see where you were going, Ava. Thank you. You were just ahead of me. All right. So I am inside a thread. I'm not inside this function anymore. So by being inside this thread, I don't really have a choice. I have to unwrap. And that means if somebody else panicked for some reason and I get the lock after them, then I can't do anything. I can't make a good decision. I can't continue. I can't ignore because I don't know. I'm here to increment that value, and that value, we don't know what state it's in. So my only response is to panic as well, which will also keep that guard poisoned. So it's an area of the standard library that is technically correct, but also difficult for beginners. And so they're actually looking at getting rid of poisoning in their threads, which I think is probably a step backwards for correctness. But that's where the prevailing winds are currently going right now in the standard library. But yes, it's when you are holding a lock in a thread and you panic. Then what's happened is the lock itself is considered to be poisoned because you have blown up and left whatever resource that lock was guarding in an indeterminate state. There's no way for the compiler to say you are definitely in the before state, you are definitely in the after state. Like it's not an atomic transaction anymore. So all the compiler says is something happened during modification. I don't know. And because you're writing the app, we know that we're incrementing here. So we could say, oh, poison is not a problem. We could make that choice. But it's the application writer that has to make the choice of what to do if they encounter a poisoned lock. But this routine is inside the thread itself. So we don't have a choice inside the thread. So I mean, technically we could ignore it here, but we're going to just unwrap and propagate the poison because nobody is going to be panicking. Okay, so from here, we now have a mutex guard, right? We called counter, which is now a mutex of usize. We called lock on that mutex. And what did it return? It returned to us a mutex guard. And that mutex guard, if you have it, you can use it. That's the nice thing about it. So what's inside the mutex guard, you have access to it. You have exclusive access to it. So you can decide what to do. You could hold on to it for half an hour. Okay, that's going to block every other thread in your system for half an hour. So you want to be very, very efficient. Now that you have the guard, you're going to dereference the guard. That's saying look inside the guard. And you're going to say guard plus equals 1. So what's inside the guard? And if I do this more pedantically, let inner equal. It's a usize. You can see here that the compiler is telling you if you dereference the mutex guard, it gives you what's inside of it. And that makes sense. If you think about, if any of you are familiar with pointers and you dereference a pointer, you get the value, right? That pointer is, is representing. So that's what's going on here. So we're going to increment the guard. And then when we're done, because we don't want to hold on to this for half an hour, we're going to drop it. And in Rust, like other languages, C++ as well, you go out of scope. It's going to drop all the variables that are in scope, including this mutex guard. And when the guard gets dropped, that tells the mutex that whoever else is waiting in line for the next log can proceed. And it will then give out the next log to the next user. And we go, and we go, and there we go. I don't know why one pass is trying to unlock. Just run. Whoa, whoa, whoa. Come on. Just run. Okay. Now I got some errors here. Oh, I can't borrow this guy as mutable. I have to make it mute. And this guy is now trying to print a mutex, which you can't do. So we've got to lock it, which you can't do in here. So we have to do, no, we can. I mean, if it's okay. Yeah. Yeah. Okay. So there we go. We're grabbing the counter. We get the lock. I'm sorry. Yeah, that's unfortunate. It's not unsafe anymore. It's not cool, but that's okay. That's okay, right? And so now what we've got is we get that result of a guard back. So we're going to return the error if we got an error, and then we would like to dereference that. And my order of operations, I'm hoping it goes in the way I hope. You're not going to dereference the result. So we'll see. It'll tell me. Yeah, I can put brackets on it. All right. So what's it telling me now? Okay, so this error is not convertible to that thing that is any type. See, I told you there would be exceptions, and of course we found one. So just for the sake of time, I'm going to do the thing I hate to do. It's unwrap in my code, my example code. And whoa, we got to 1 million. Finally. Okay. That's the question. Like, you can't trust it yet. Oh, there's another 1 million. There's another 1 million. Now I can tell you by feel, just like how often I'm hitting the run, this is much slower. But we're not dropping 90% of our data on the floor. So, there's a trade-off, right? There's a correctness thing. If it's a time bomb with a single thread earlier. So that's true. That's true. There is another option. And we're going to touch on this briefly tonight that will give you the best of both worlds. It's almost as fast as the crazy data race scenario, has less complexity. Well, I shouldn't say that exactly. It's less in your face, right, than this mutex. There's other kinds of locks, I should say, for completeness, right? So we're going to lock, then we read, we modify, then we write, then we drop the lock. So everybody can see why we now get the correct answer, right? Any questions about that? Yes. That's right. Every one of those threads, the first thing it does is calls count or mutex.lock, right? That's what our code says to do. So they get spawned. And, once they get spawned, they start counting to 100,000. But the first thing they do is they call mutex.lock. And the mutex says, I hear you, but the guard has been given out. And it has an internal flag that it uses to indicate whether or not the guard is available for somebody if they want it, or whether the guard is in use. The guard is currently in use, so all of the threads that call into the mutex are going to block. They're just not coming back until the guard releases. If you never give up the guard, you've just deadlocked your application, right? Rust will not protect you against deadlocks either. It's not fearless deadlocking. You can deadlock. But it's not undefined behavior. You haven't given over your system to the bad guys. And that's what they're protecting against. It's not a memory safety violation to deadlock. But that's how mutex works. It's going to hold everybody up in a queue until that guard comes back, and then the first person in the queue will get that lock, get that guard. They can do what they want to do. They give it back, then the next person, and hopefully you get through the whole queue in a reasonable time. Yeah. Yeah, I mean the same thing when you read a file, right? It's a standard OS blocking mechanism. It's OS specific. So there's a part of the standard library that breaks out for Windows, Mac, Linux, and all the other supported OSs, and they use the the operating system's blocking methods for that.
But when you have 100 threads calling lock, they prevent the data race inside the lock. But a race to lock the mutex, how do you prevent that?
Ah, yes, that's an excellent question. Does everybody understand the question? If you have 100 threads or 10 threads or whatever trying to access the lock, how does the standard library prevent the data race we just saw from happening at the level of the lock? Okay, so all we're doing really is we kick the can down the road one. I think that's an excellent observation, Nate. Right? We had a data race on our usize, right? On our flag, whether it's a usize or a bool, it doesn't matter, right? It's a resource. Well, now we have 100 threads or 10 threads racing to get the lock. Well, what if we have a read, modify, write data race on the lock? Like, how are they implementing the lock so that they don't have a data race? That is, in fact, where we're going next. So it's a great question. Yes. Say again about containers? Yes, this mutex is thread safe. In fact, any type in Rust that implements the there's something called a trait in Rust. And you could think of a trait as an interface from other languages. And any type that implements the sync trait is safe to use automatically, is safe to use from multiple threads. So there's lots of documentation here, and it says like who implements trait in the Rust standard library. Well, there's all these types, and if we go way down, we're gonna see mutex in this list somewhere. Okay, that's what we just used, mutex. So you know it's safe because it's, remember synchronization primitives? It implements the sync trait, which means it's safe to use across threads. How do you implement that trait? Not a beginner answer, or not a beginner question. Yeah, it's an unsafe trait. So if you were going to implement your own, you can do that. But for those who are curious, look at that. Yeah, the sync trait is unsafe and doesn't contain any code. So it's a marker trait. Yeah, go ahead. Yes. So what Ava just said was if you create a new type and every field in that, say it's a struct, every field in that struct is sync, Rust has something else called an auto trait that will automatically make your type sync as well. So you don't have to make it sync yourself. So you get it for free if everything that is inside your type is actually sync. Can you write your own auto types? I don't think so. I don't think so. I think auto type is a there's a blanket, there's an auto or an auto type or an auto trait, and then there's a blanket trait. You can write your own blanket traits. So you can have a blanket implementation that says, hey, anything that has this attribute gets this behavior, even if you didn't write it. So you can add extension traits or extension methods. You could do all that kind of stuff in Rust. But an auto trait, I think, is special to the compiler. The sync trait? The sync trait? The sync trait is just a marker. It's just a flag that says whoever implemented the sync trait on this type is swearing that it is safe to access this for multiple threads. The compiler, it's unsafe because that tells you the compiler can't guarantee that. It's up to the implementer to guarantee that. That's what unsafe means. Right, because it's unsafe, if you just say implement sync for my type, it's going to be unsafe and it won't compile. So then you have to do what I did earlier and use unsafe everywhere in your code. And if you're not upholding the guarantees that the Rust compile, you'll get undefined behavior. But what Rust is doing is it's making it explicit. If you're looking at a whole bunch of code, you can zero in exactly where your undefined behavior comes from. It must be from within an unsafe block, because Rust makes this guarantee with an asterisk that a very small one though, that if it's safe code, you can't have undefined behavior. Thank you. That's a very good point. It's a flag for the compiler to know what can and can't be used in certain contexts. It doesn't show up in your assembly at all. Right. And the same is true of the borrow checker. A lot of people think that the borrow checker is like a mini garbage collector that has runtime overhead. There's nothing in the code after it's done compiling that's borrow checker. That's all done at compile time only. Okay. Thanks. No, I didn't realize that was your question. That's a great question. Okay, so I'm going to quickly move to the next step here to say, how can we recover both speed and accuracy and correctness, and answer Nate's question earlier about how does lock do it? So there's another way we could actually implement this, and this is using something called atomics. Dun, dun, dun. Exactly. It sounds like we're weaponizing this stuff here. Okay, so we're using a usize before, and you could see that there was atomic for every different numeric type. Now, an atomic is a data type where the hardware, your CPU, guarantees that a read, modify, write cycle cannot be divided. That's why it has the name atomic. So if you can push this read, modify, write problem into the hardware, then the OS and the software can ignore this problem, and you can have a data race on an atomic, and the hardware will sort it out. So to answer your question, how do we avoid the data race in a lock? They use an atomic bool. They use an atomic semaphore to indicate whether the guard has been given out or not. So everybody can race. The hardware will sort it out. So we can say, well, why don't we do that? So let's try. Okay. So we're going to make an atomic usize, set it to 0. And watch how clean this gets. We're like, okay, here we go. No, because the hardware is going to do it for us. So we're going to have this counter, and we want to increment this counter. It's not a mutex anymore, so it's not a guard. So we can get rid of all this guard code. We don't need that. And we'd like to say counter plus equals 1, right? That's the read, modify, write. Because I should say counter equals counter plus 1, right? When I say counter plus equals 1, that is shorthand for this. Okay, so the read is taking the counter here on the right-hand side of the equal sign. The modify is adding 1. And the write is assigning this value back to the memory. Okay, that's your read, modify, write. So I should have mentioned that in case people weren't familiar with that Rust shorthand. But this includes a read, modify, write in software land. But we just said that an atomic takes the read, modify, write into hardware land. So how do we tell the hardware that we'd like it to do a read, modify, write? The API changes. So we can't do it this way, as you can see. It says actually, counter. It shouldn't say that. It should be a different error. Okay, whatever. Yeah, I was thinking you can't have atomic usize doesn't implement add is what I would have thought it would say, but doesn't matter. It's like, no, that's not how you do it. We're going to use something called fetch. So you can see it's right in the method name. The fetch is the read, add is the modify, and presumably it'll write it back. So if we read the docs for this, it says adds to the current value, and it returns the previous value just in case you were interested or needed that for some reason, for logging or whatnot. We're going to throw away the previous value. But what we're going to do is we're going to fetch add 1. So we're going to fetch add 1, and it implies put it back into the atomic variable. There's this other parameter here called ordering. With respect to ordering, you've got, this is why I hesitated when I said atomics are simpler than locks. Not anymore, they're not. So for anybody who's curious about these are called atomic fences. And we are definitely not going to touch these today. They're very complicated. But what I'm going to do is I'm going to simplify these for you and say, when you use atomics, until you feel like, you're ready to take the training wheels off, always use sequentially consistent ordering. That's it. Nope. It's a lot more complicated than that. Yeah, atomic fences are. Yeah, it's a very complicated topic, and there are compiler fences as well, and so it's extremely complicated topic. It's a very advanced topic. But if you use sequentially consistent, you may be leaving a little bit of speed on the table. I mean, a little bit. But you will be correct under all circumstances on all platforms. You do not have to worry about it. So if you just want it to work, start with sequentially consistent, and someday when you get curious, you can go and look at acquire ordering and release ordering and all the other things, and you'll be like, okay, I'm going back to sequentially consistent. Okay, but our locks are gone, our errors are gone, our poisoning is gone. It's all gone, right? And when we run this, well, we got to print it, right? Let's see, how do we read it? Get. Load, thank you. Yep, and you need an ordering, of course, because it's an atomic. And so there we go. This, with all that crap out of there, no errors anymore, no unwraps, gets us 1 million. And if we keep running it, it's still 1 million every time. And I can assure you this is a lot faster. If we were to benchmark the different implementations, the atomic implementation would be much, much faster than the mutex implementation. Okay, not to beat down on mutexes because they're very useful. There are flavors of mutex. We just used mutex. There's also another one called a read-write lock. So you can have multiple readers accessing at the same time. But as soon as a writer says, I'd like to get write access to this, all subsequent read requests to that lock queue up behind the writer. Even though it would be perfectly legal to let those readers go first, you would starve the writer. The writer would never get access because presumably more requests could keep coming in to read. So the way the read-write lock works is that all the readers get access immediately when they ask for it until a writer asks for access. Then all the readers that come in subsequent to that queue up behind the writer. When all the readers who have access drop, all of them, so there's now 0 users of that resource, then the writer gets to go. The writer does its thing. Then all the readers who came in after the writer see the new value. And temporally, they actually ask to read after the write asked to write. So you Hello. Okay. Holy moly. Yes. So what ends up happening is that the read or sorry, yeah, the read that followed the write actually sees the updated value, even though that didn't happen until way after those requests were sent to the log. I think, that's really cool. I think that's a good introduction to sort of why we have locks. Locks come in different flavors. And then eventually, if you want to get a little fancy and can be easier to use, you can also use atomics as your synchronization primitives. Carl? Yep. Right. Right. You can't have an atomic on, say, your particular struct. I mean, there are ways to do it, but they all come down to mutexes underneath anyway, because atomics are really about the hardware. And so the hardware doesn't know about your giant data structure. Nate?
So in this case, you're have this like, it's gonna take a few seconds for me to, after I read it, I want it to not change before I write something back.
Yeah, so the question was, with an atomic, you sort of read it and write it all at once. Whereas with a guard, you can hold it, go out to lunch, have a coffee, come back and do whatever you like. And you can hold it. With atomics, can I hold the atomic? All by itself, you cannot. So what you do is you're actually sending the hardware an instruction. Okay, with an atomic, there's one write occurring. You don't know what the original value is. In fact, that's why it returned the old value to you after you wrote it, because you don't know what it is. So what you're saying is you send a command to the hardware. It's actually an x86 or an ARM assembly language instruction that says add 1 to whatever value is in there. And so it will go ahead and do that. And because you didn't get a chance to read it first, the hardware will read it, modify, and write. But because you in the software level didn't get to read it first, it will at least return to you the old value. Because you might say add a random amount. You don't know what was in there before, and you might care for some reason. So you could load it first. But as soon as you've read it, the way we're printing it out on screen, as soon as you've read it, even before it made it to the screen, somebody else could have come in and changed it. So your data is immediately out of date. So if you want to prevent any updates to that resource for some duration of time, then you have to lock it. Does that make sense? That's it.
My mind's, how to
Yeah, the hardware, you mean?
well, how do you guys think of it? Sounds like, I don't know, it's, anyway.
The
answer
is use it.
Yeah.
Go for the source.
Yeah, you can use you can implement a lock by using a mutex. Like if it's a very simple implementation, you just have an atomic bool, right? You have a request come in, somebody calls the API, and all you have to do is acquire that mutex, not the mutex. You look at that atomic bool, right? So
You look at it, it's false right now.
Yep.
They look at it.
Yep. Oh, I see what you're saying. Yes, you can actually conditionally increment, say, a value or conditionally change a Boolean. And you can one instruction, right? And you'll say to the Boolean, turn yourself to true if you are false. Otherwise, don't do anything. And that instruction will return success or failure.
Okay, so
Only one person will get the success because the hardware is enforcing that. And so, they're called conditional access loops. Yeah. Right. That's right. That's right. All the other 99 threads will continue to loop and say, oh, okay, how about now? How about now? How about now? Right? This is the most simple, wasteful way to do that. But they could spin spin on this. If you wanted to look into this more, look up CAS loops, conditional compare and swap. Thank you. It's a compare and swap loop is a basic way to do this. Okay. Does anyone else have any questions? Yes, sir. Thank you. Thank you. The comment was, I implied it earlier, but just to make sure everybody got the message, don't use static mutes. Static mute's bad. All right. Thank you, everyone. Yeah, I think we'll transition over to Jack. We don't have a ton of time, so if anybody needs a quick break or a quick drink, please go grab it now, and we'll get set up for Jack's talk. Yeah, sorry about this microphone, this janky microphone setup.
Yeah, what do I have to? Oh, okay, that's something. That's something. All right. So if I drag this over here, but then I can't see it. So yeah, I gotta do. Uh-oh. Now I gotta here. Mirror. Why? Will it work? Okay. The time is quite tight, so I will just launch in without waiting for everything. So everyone can see this? It's okay. It's okay. I'm kind of launching in rudely myself. Can everyone see this? It looks blue to me on the screen. Okay, and it looks like maybe some digits are cut off, but those aren't important. So okay, cool. So I want to talk about async Rust. Async Rust is a famously very complicated subject. There's a lot going on, and so especially since we only have a hair over 10 minutes, I just want us to like kind of dip our collective toe into the water of async Rust. I just want to kind of like motivate it a little bit. And my hope is that when we go get pizza, hopefully as a group, a bunch of us will probably go to Slapstick. And if folks think this is interesting and want to keep talking about it or see some more demos on the laptop or whatever, I'll have my laptop. So I just hope to provoke questions. Luckily, Brad has teed me up exceptionally well, because we're going to start this whole thing by talking about threads and doing things in parallel, and some of the limits we run into, because that's kind of how we arrive at this question of why do we care about async? And that's really the question that I want to talk about more than what is async, because the question of what is async is long and complicated, and it's hard to even launch into that unless we already care about knowing what it is. So let's get there. So I have some code on the screen. It's a very silly program that does a very small amount of work. I'm going to run it first. So I can say cargo run, and I've defined multiple binaries. So I'm going to have this little fancy way of running it. In fact, I'll show that since this is for beginners. So this is my cargo.toml, and I'm doing a slightly unusual thing, which is that I have a bunch of binaries in the same project. And you don't have to worry about that, but that's where you're going to see me use the bin flag. And this first one here is called serial. So I run it, and it's going to print 3 dots to the screen in 3 seconds, and that's pretty boring, and that's fine. And I can also say run it like this, and I'll do this for most of the next 10 minutes. Same program. So when you say cargo, I think I have it in my history. Yeah, the cargo build release puts all the binaries in target release. So I can just find them there. And that's a nice way. I can also time my binary. That's the standard little bash time thing. And that prints out, okay, that took 3 seconds and did not use much CPU. Cool. So it's just printing some dots. Obviously, this is just a tiny little example to get us started. So work, sleeps for a second. Standard thread sleep is the normal way we sleep in Rust. Sleeps for a second, prints a single dot, and then probably half the room has seen this little nonsense I have to do because I want to see that dot immediately. I don't want to wait for the new line, so I have to flush standard out. And if you haven't seen that before, it's trivia. Don't worry about it. But when you like to print out little dots on one line and see them immediately in the terminal, you need to flush. Ignore it. So then my main function goes work, work, work. And I finally print the new line. This print was not println. This is just print. So there's no new line there. And so that's why I got ... on the same line. Okay, great. So this program takes 3 seconds to print 3 dots, and that's silly. And Brad just taught us how to use threads. And so it might be very natural for us to want to speed this up. Hey, maybe if we run 3 threads, it takes 1 second, right? And it does. So we are now all experts in this code, right? So this is exactly what we just learned. We thread spawn. And in this case, I'm just doing 1, 2, 3. I'm not even doing a loop. Join, join, join. This one is called threads. So I should be able to see it like this, and it's going to run in 1 second because it does all 3 of those things at the same time. And we're all now complete world experts in what all that meant. So that's great because we have very little time. So then, as this scales up, obviously we don't want to write variables. If we get 100 threads, we're not going to write 100 variables. I'm going to do what Brad did, right? We have a loop. So threads 100. So now, again, work has not changed, but I have a vector, a list, and I'm pushing the threads in, and we just saw it, and that is so great. So now I'm going to run 100. What did I say I was doing? Yeah, I guess we're going to print 100 dots. So we can see that. So it's not printing 3 anymore. It's going to print 100, but it's still just going to take 1 second. We can see it took just a hair over 1 second, that 1.009, and it printed 100 dots. And that's great. And then where Brad went with that was all the interesting questions that come up when these threads want to share data and coordinate with each other. And I'm going to go in a totally different direction. So obviously these threads are not sharing any data at all. There's maybe some coordination under the covers when you print, but no one cares about that. That's implementation details. What I want to do is get really silly, right? And like what if we do a lot of threads, right? So I think I should probably show the code. So all I'm doing is changing the number 100 to 20,000, which is a random but not entirely random number. And when I try to print 20,000 dots on 20,000 threads, it doesn't work. It doesn't work. It prints a bunch of crap. This is a panic. It's resource temporarily unavailable. I don't actually know. It could be that we ran out of thread IDs. I kind of doubt it. I think it's probably more likely that we ran out of memory to allocate for thread stacks. It doesn't really matter why. It's just, you just can't do that. You shouldn't do that. Yeah, I probably have to configure ulimit to I have no idea. I don't even know. And if you try to run this code on the Rust playground, which you can do, you'll see that they run your code in an environment that is very tightly limited. I think about 500 threads starts to trigger this panic. So yeah, I got pretty far. Yeah, I burned some CPU before I died, so that's cool. But I can't do this. And so this is and those of us who've worked with threads before probably know that spawning 20,000 threads in a loop is not a great idea, no matter the circumstances. Even if we succeeded, this code actually runs. If you run it on Windows, it does work. It's just horrendously slow. I think they block thread spawn until I have no idea what they do. But this is not a good idea, right? And folks who've seen threads before probably saw me starting to do this and knew that it was not a good idea. We could try to compromise and use a thread pool. Probably a lot of people in the room know what a thread pool is. Maybe you spawn a small number of threads and they get some sort of job queue, and we can do that. I'll just look very quickly. The details don't matter super much. Work is the same. I'm using Rayon Scope. It is a threading library. This so happens to create a thread pool for us, and I'm not going to worry about the details. But when I run this one, let's just do it this way. Target, release, Rayon. It doesn't crash, which is nice. But yeah, we can see that this is not going to work, right? The Rayon thread pool, I have 8 cores on this laptop, so by default, the Rayon thread pool spawns 8 threads, which is a very reasonable thing to do if you want to efficiently use the cores. But those 8 threads are only going to be able to do 8 sleeps in parallel, and so I'm never going to make it to 20,000, right? So yes, I've prevented the crash. My program, in theory, would eventually complete, but this is not going to work. So if I have 20,000 or more things to do, and those things all require waiting. In this silly example, that's because I'm sleeping. But of course, on the internet, we do a lot of waiting, right? I might be making a network request. There might be some latency. I might want to make 10,000 network requests. My CPU is going to spend most of its time waiting for each of those. We can't use threads to get that much concurrency. It just doesn't work. And that is what pushes us to sort of look for newer, greater, more interesting, and more complicated things. And we kind of wind up doing some of this. And now we see async code on the screen, which I am not even going to begin to explain. I'm just tossing it on the screen. It's extremely rude of me to do this, but I'm just like throwing a bunch of crap on the screen. I mean, it looks similar, right? There's the sleep and the print. Okay, fine. And there's a loop, and this is totally different, whatever. But it's 20,000, so okay. And I can get over here and I can run it. I think, let's see here. What did I call it? I call it Tokyo 20K. And wow. I think go 2, 3, 4, 5. Yeah, so I think that's yeah. So right, we can time it. So yeah, time. I'll get that back to a reasonable size. If I time it, that's just a hair over 1 second. And if we want to check its work, we can pipe that into word count. Count the number of characters for me, please. And we will see 20,001 because of the new line, right? And so, damn, cool, right? And like, how high can we like? Can I do 1 million? Like, yeah, I can do 1 million. And at this point, the printing is taking longer than anything else, which is why it takes like 2 seconds. I think. Yeah, if I do it to dev null, maybe it might be the fastest way to do it. I wonder. Yeah. The fact that I'm doing that flush was great for like having the dots appear nice in the demo, but like it's definitely tanking my performance because I'm making at least 2 system calls. Anyway, it doesn't matter. Like 2 seconds is pretty good for 1 million tasks. They're all sleeping, right? And so, cool. So maybe should we like learn what's like? This is neat. So we can look at it. I'm going to go back to the simplest possible version that does not even include the loop. So remember, we started with serial.rs, which is just work. So if we want to do just the equivalent of that, I have Tokyo serial here, and that's just work. And so this is a good way to kind of get our bearings, at least. So I'm going to just switch back and forth rapidly. So just like that. So I don't know if that shows. Yeah, that shows up on the monitor. So we can kind of see what's happening. I probably should have like used a diff viewer or something, but anyway, like, so the functions all become async functions, and every time we call an async function, we put .await on the end, and this macro is doing some magic. Okay, and the sleep is an async function too. We can tell because we see that we're awaiting it. So okay, well, whatever that means, and then go back to the 20K version. And we see, okay, so it's similar to making that vec of thread handles. We have a vec and something's going in there, and I've called it futures, and that's not like a normal way to use that English word, but like, okay, these are futures, whatever that means. And we can see that we're actually, let me go back to threads 20K. So when we were calling thread spawn, just like Brad taught us, of course, we didn't put the paren here when we referred to work, because that would call work immediately. That would have done the work on the main thread, which is not what we were trying to do. We use the function pointer for spawn, and we can see that with the future, we do put the paren on there. So that's a little different, but we do not put the await on the end of it. So we're somehow accomplishing a similar thing. Some sort of deferred work or indirection is being done here, and it has to do with await. You can kind of see that going on. Okay. And then whatever join all is kind of causing it all to run. There's one very quick thing with my last 2 minutes I want to show. It's again just to kind of like provoke interest, because we don't have time. What I would truly love to do is start translating every little piece of this into normal functions, like not async, no magic, right? Start like actually like replacing this with the synchronous version so that we see what's actually going on. And we don't have time. That's like an hour and a half talk, which I would love to write. I haven't put it together yet, but we can do one little thing, which is kind of like a mistake, really. I'm calling it Tokyo blocking. So if I'll do the back and forth thing. So you can see what I'm doing. Get rid of that cursor. Yeah. So my mistake is that I have used the regular sleep in my async program. This is a, unfortunately, somewhat common mistake, and it's one of the things that is like difficult about async. But it is interesting to look at what that does. So again, this was the good version that used the async sleep correctly, and we saw that what did that do? That just like filled 1 second, and you got all these dots. If we do the bad version, I call it Tokyo blocking. So now it's the same code, but I did the synchronous normal standard thread sleep. That, well, it's working, but it's going 1 dot at a time. So we're kind of just starting to peer into what's going on here. And we're saying like, okay, if I sleep that thread, then that blocks everything else. So what that's telling us is one of the really interesting things about async, which is that we have all these tasks or futures or whatever buzzword, 20,000 of them or 1 million of them. And somehow we're running all of those things on one thread. Not always one thread, but in this case, they are all running on one thread. And if we block that thread, then that stops them all from running at the same time. It's very interesting. So whole big topic, and we've only just started to scratch it, but that's what async code can do. It's why we care about it. It's a hint at how complicated this is about to get and how easy it is to make mistakes. But there's a lot more to say here, and hopefully someday we'll get to do that talk. So thanks, guys.